Hello, I'm Haneul Kim from IXLF. Today, I would like to talk about the topic of articulated tool manipulation with dexterous hands. This topic starts from the question of whether a robotic hand can go beyond simply grasping objects and instead use tools to perform more complex manipulation tasks. In particular, I focus on tools whose shapes change during manipulation. These are called articulated tools. In this context, I will introduce one representative paper, Hierarchical Reinforcement Learning for Articulated Tool Manipulation with Multi-Fingered Hand, published at IROS 2025. When we talk about manipulation tasks, there are many different types of problems. Here, I organize them along two main axes. The first axis is the type of end effector. Some tasks use dexterous hands, while others use simpler grippers. A dexterous hand has many degrees of freedom, so it can perform much more diverse and complex manipulation. However, because of this high dimensionality, it is also much harder to control. In contrast, a gripper has a much simpler structures. The second axis is the type of task. Some tasks focus on simple grasping, while other involves two use on top of grasping. The problem I focus on today lies at the intersection of these two axes. In other words, it is a tool use task performed with a dexterous hands. So this area is particularly challenging because it involves high dimensional control, complex contact dynamics, and simultaneous interaction among the hands, the tools, and the object. When we hear the term dexterous manipulation, we often think of tasks where a robotic hand directly grasps an object or rotates an object inside the hand. However, once we introduce tools, the simulation situations change significantly. By using tools, the range of tasks that a robot can perform becomes much wider. Humans also do not rely on their fingers. So we use tools such as chopsticks, tweezers, and scissors to perform much more precise and diverse manipulation tasks. So here, tools can roughly be divided into two categories. The first category includes tools like hammers, while the main requirement is to hold the tool and swing or move it. The second category includes tools like chopsticks or tweezers, which require precise real-time manipulation. In particular, tools such as tweezer and scissors continuously change their shape during use. This means that the robot must continuously control initial states, such as how widely the tool is opened. The tools that change their shape during manipulation are called articulated tools. Therefore, to manipulate these tools, simple position control is not enough. The robot must also be able to control the shape of the tool itself in real time. So based on this problem setting, the paper I introduced today directly addresses articulated tool manipulation in a dexterous hand environment. The core idea is not just to make a robotic hand hold a tweezer. Instead, the robotic hand must use its finger to control the opening of the determines manipulation performance. Therefore, the central question of this paper is as follows. Tweezers coordinate with the robotic arms to move toward the objects and finally pick up a small object. For these tools, position alone is not sufficient. The internal shape of tools such as how widely the tweezer is opened directly. Can a robotic hand go beyond simply holding a tweezer, control the shape of the tweezer within its fingers, coordinate with the robotic arms to move toward the object, and then stably grasp the small object? So the system consists of a robotic arms, the multi-fingers robotic hand, and a tweezer like articulated tool that is already fixed in the hand. The goal is to use this tool to pick up a small object from a table and move it to the target positions. An important assumption is that the paper does not learn tool grasping itself. The authors assumes that the tool is already stably fixed in the hand at the initial stage. So the focus of this work is not on how to grasp the tool. Instead, the focus is on how to control the shape of an already grasped articulated tool and how to coordinate the arm and hands to pick up an object. The authors emphasize three main challenges. First, there is a dynamic shape adaptation. The robot must precisely control the opening angles of the tweeter using its finger. Second, there is a visual perception. From the point cloud, the system must estimate the pose and shape of the tool, as well as the position of the objects even under occlusion and sensor noise. And third, there is a arm-hand coordination. The arm is responsible for gross motion, such as moving the tool near the object, while the fingers are responsible for fine motion, such as adjusting the opening of the tweeter. These two control problems must be coordinated at the same time. So this is the overall framework. The hierarchical goal conditions reinforcement learning. First, the high-level policy is responsible for the overall task. So it decides how the robotic arm should move in order to transform the objects to the target positions. And it sets a goal shift for the tweeter, such as how widely the tweeter should be opened. Then the low-level policy executes this goal. Given the target tool shape specified by the high-level policy, the low-level policy decides how to move the fingers so that the tweeter reaches that target shape. Let's first look at the encoder pre-training stage. The key problem is that the low point cloud contains both position and orientation information mixed together with shape information. So because of this, it is difficult to directly learn the shape of the tool from the low point clouds. To address this, the method first use SVD-based point cloud registration. So this computes the transformation between the input point cloud and a canonical point cloud. And through this process, the current pose of the tweeter can be estimated. At the same time, the point cloud can be aligned to the canonical frames. So the reason for this alignment is to allow the encoders to focus on the shape of the tools rather than being affected by its position and orientations. And additionally, by comparing the transformation with the previous time step, the method computes the linear and angular velocity of the tools. So these values are later used as the part of the tool set. So in short, this stage separates pose from the point cloud so that the remaining representation can focus more directly on tool shape. And the robot needs more than just positional information. It must know shape information such as how widely the tweeter is opened. However, low point clouds are incomplete and noisy. So instead of directly using this from the low point cloud, the paper trains an encoder to learn a stable representation. The training data consists of about 10,000 synthetic point clouds, and they remove about 20% of the input points to simulate occlusions. And then they also apply random rotation and translation to generate different poses. And then the paper uses a point net based encoders. So the input is the aligning point clouds and the output is the latent representation jet. This latent variable jet compactly represents the shape of the tweeter, especially information related to the opening wise. And then the decoder then reconstructs the point cloud from this latent variable jet. So through this process, the latent space is encoded to represent the actual shape of the tools. The important point is that this latent variable jet is later used as the goal space for the low-level policy. So, in summarize, this stage is not just simple of feature extraction. It is a representation learning stage that converts the shape of the tool into the form that can be used by reinforcement learning. Now, let's look at the low-level policy training. When the high-level policy gives the goals such as make the tweeter into like this shape, the low-level policy moves the finger joints to match the shape of the tweeter to that goal. So state of the low-level policy consists of two parts, the tool state and hand states. So it's completely represent how widely the tweeter is open and what shape configuration the tool is currently in. And the hand states consist of the current joint angles and joint velocity of the hands. And then the action is the change in the hand joint angles. Like the policy does not directly output the absolute next joint angles. Instead, it outputs how much each finger joint should bend or extend from its current positions. So the next target joint position is then computed by adding this action to the current joint angle. And the low-level reward consists of two parts. And first is goal reward. This reward becomes larger when the current latence shape of the tweeter, ZT, is closer to the target latence shape, Z goal. And then the second part is the effort reward. This reward is designed to reduce unnecessary motions, so it penalizes two things. The first is excessive movement of the overall tool pose. When humans use Twitter, we do not shake the entire tool excessively, so we keep the tool stable in the hand and adjust only the openings. And it penalizes large tool velocity and angle velocity, which would indicate that the overall pose of the tool is changing too much. And second penalty is for excessive finger joint velocity. This prevents the fingers from moving too aggressively. And then let's move to the high-level policy. So while the low-level policy controls the shape of the tweeter using the fingers, the high-level policy decides where the robotic arm should move and what shape the tweeter should take in the current situations. So the tool states and the high-level states also consist of two parts: the tool states and object states. And the action has two components. The first is target latence representation that goals. And the second action is the movement velocity of the hands or robotic arms. And this value is used to move the robotic arms toward the objects or to move the objects toward the target position after grasping. And the reward consists of sparse rewards and a dense rewards and a penalty. The sparse reward is given for the final success, and the dense rewards continuously encourage the tool to move closer to the objects and the objects to move closer to the target positions. And finally, the penalty is given when the tool and objects becomes too far apart or when unsafe situations such as collisions occurs. And this paper, training high-level policy through a random exploration alone is extremely difficult because the task involves complex context interactions. So, to address this, the paper first used the handcraft controller to generate a replay buffer. So, for example, it has access to the exact positions of the tweeter endpoints and direct control commands for the tweeter joints. So this controller operates in 4 steps. First, it moves the tweeter towards the objects. And second, once the tweeter's endpoints are close to the objects, it closes the tweeter joint. Like it reduces the opening of the tweeter so that the object is enclosed by the tool. Third, when the inner wires of the tweeter appropriately match the object size. The system considers the grasp to be stable and moves the tweeter towards the target post. And finally, it stores the state, action, and trajectories from this process in the replay buffer. So, the high-level policy then uses this replay buffer to learn much faster. In other words, the privileged heuristics policy does not replace the learned policies. It reduces the difficulty of explorations. So, thanks to this component, the high-level policy can more stably learn hand-arm coordinate trajectories that would be very difficult to discover through random trial and error alone. So the graph on the left shows the success rates for four object shapes: a sphere, cube, cylinder, and tetrahedron. So the important distinction here is between single grasp and multi-grasp. So a single grasp means that the robot succeeds on the first attempt, and multiple grasp means that the robotic is allowed to try multiple times. These results show that the average success rate on the first attempts is about 54%. And with multiple attempts, the success rate increased to about 70%. So the policy shows a certain degrees of generalizations across different object shapes. And even without direct object geometry inputs, the system can grasp different subjects by generating diverse tool shapes. And failure, this result means failure is not always meaningless. As the paper explains, a failed first attempt can sometimes change the pose of the objects, so making it easier to grasp in the next attempt. And the image on the right shows failure case. The first failure type is inaccurate object position estimations. If the object position is not estimated correctly, the tweeter moves to the wrong locations. And the second failure type is slippage caused by the insufficient grip force. If the tweeter does not close firmly enough, or if the lobes lift the objects before achieving a stable grasp, the objects can slip and fail. So this reveals an important limitations. The current system uses visual information only without tactile sensors. So it is difficult to adjust grasp force or response to slippage in real time. And the graph on the left shows the ablations results for the low-level policies. So blue curve shows the result with the effort reward, and the orange curve shows the result without the effort reward. So when the effort reward is included, the policy converts much faster and reaches a higher final success rate. And if the entire tweeter shakes too much or if the fingers move excessively, stable manipulation becomes difficult. And the image below show the low-level policy executing different latent goals. And next, the graph from the right shows the results for the high-level policy. So the first is whether the privileged replay buffer is used. The second is whether the hierarchical structure is used. The blue curve shows that when the privileged buffer is used, learning becomes much faster and reaches a much higher cumulative returns. In contrast, the orange and green curve shows that without the buffer or without the hierarchical structure, and learning barely progress or become much slower. So these results give an important message. This problem cannot be solved effectively through simple random explorations, and it requires a structure that provides useful trajectories in advance. So let us discuss the limitation and future direction. First, the method assumes that the tool is already fixed in the hand. This is a strong assumption. It means that the first step of the real pipeline, how to grasp the tool, is not included. Second, because The system performs grasping using only visual information without tactile feedback. It has limited ability to adjust grip force or response to slippage. And second, the method is specialized to a single Twitter-like hinge structure. So it has not yet been verified whether the approach generalizes to many different articulated tools. This limitation directly suggests future research directions. First is to integrate tool equations and manipulations. The current work focuses on using a tool that is already grasped. However, in real environments, and the how the robot grasp the tool strongly affect later manipulation performance. And second direction is to introduce tactile-based control. For articulated tool, contact and force transmission are central. The second is tool generalization. Instead of handling only on one tweeter, a single policy should be able to manipulate tools with different hinge locations, stiffness values, and shape. This naturally connects to online systems identifications or latent inference. To summarize, the significance of this paper is not simply that the robot successfully used tweeters. More importantly, the paper expands tool use from a geometry-centered problems to a functional state problems and connects this idea to hierarchical reinforcement learning and latent representation learning. At the same time, future work should build on this structure and move toward a complete pipeline that includes tool grasping, tactical control, generalizations, or even a diverse tools and long horizons task decompositions. Thank you for listening.